In this question it says, suppose a current of 150 amps flows through a copper wire for 12 minutes. Calculate how many moles of electrons travel through the wire. So in order to solve this, we need to use the same equation as the previous question on this playlist, which is Q, the charge, equals I, the current, times T, the time. In this case, we're trying to find charge. So Q, the charge, equals I, the current, which is 150 amps, and an amp is a coulomb per second, times T, but the T, the time, has to be in seconds, not in minutes. So you have to take the 12 and divide it, or multiply it by 60, because there are 60 seconds in every minute, and you find out that 12 minutes is 720 seconds. So when you do all this math, you get Q equals 108,000 coulombs. So this is the amount of charge that we're going to transfer at 150 coulombs per second for 720 seconds. We then also need to use Faraday's constant. And Faraday's constant, F, is 9.649 times 10 to the 4 coulombs per mole of electrons. And what this means is, if we use dimensional analysis, that 9.649 times 10 to the 4 coulombs of charge is equal to 1 mole of electrons being transferred. So if our ultimate goal is to find the moles of electrons, in this case, we want to use the 108,000 coulombs times, well, we want coulombs on the bottom so they cancel out, 9.649 times 10 to the 4 coulombs on the bottom, and 1 mole of electrons on top. And when you do that math, you find out that this is 1.12 moles of electrons that were transferred in order to transfer this 108,000 coulombs of charge. So that is basically how we would solve this problem. I do want to look at one more example because although it's kind of just rearranged variables, it does look somewhat different, so I did want to give you a second example. So in this case it says, suppose 1 mole of electrons must be transported from one side of an electrochemical cell to another in 182 seconds. Calculate the size of the current that must flow. So we're essentially going to use the same equations, but in this case we're starting with the moles of electrons. So we're starting on the opposite end, which is why it's the same problem backwards, but it doesn't look exactly the same, so I wanted to go over it. So in this case we're starting with our 1.00 moles of electrons. We again want to use Faraday's constant and the relationship that 9.649 times 10 to the 4 coulombs equals 1 mole of electrons. You don't really have to do the dimensional analysis here because this is 1, but if we wanted to, we could put 1 mole of electrons on the bottom, and 9.649 coulombs, times 10 to the 4 coulombs, that's a time sign, times 10 to the 4 coulombs on top, and of course it's just 1 times this divided by 1, so it's the same number, which is 9.649 times 10 to the 4 coulombs. We now can use the same equation. Q, the charge, equals I over T. But in this case, we're trying to solve for I, so divide both sides by T, and we find that I, the current, equals the charge divided by the time. The charge for the 1 mole of electrons that was transferred using Faraday's constant, and of course is Faraday's constant because it's 1 mole, 9.649 times 10 to the 4 coulombs, divided by the time, which is already given in seconds, 182 seconds, and rounding to 3 sig figs, we find out that this charge is 533 amps. So this is basically exactly the opposite of the previous one. Here we started with moles of electron and we were asked for the current. In the previous case we were given the current and we were asked for the moles of electrons.